Okay, so this is a pretty exciting lecture because we're going to be getting into statistics, talking about standard error of the mean and the normal distribution. These are I guess we're getting into statistics in its proper form. We're going to be talking about confidence intervals, t-tests, all the things you'll need to do to really analyze your data. We have our background now of how to design an experiment, and we have an understanding of probability and how to talk about distributions and spread. But now it's time to start thinking about how we can tell means apart and compare different distributions. And that's where the standard error of the mean and the normal distribution become really important. And at the end of the lecture, we're going to relate these concepts back to cells and RNAs and proteins and why the normal distribution is so prevalent in biology. But first, we're going to go back to our hard and dry sampling from a population. So in the past, we've learned that if we have a population, that population is going to have a center described by a mean and a spread described by a standard deviation. And if we sample from that population, we will have subsamples that each have their own center described by x bar and their spread described by s, which is the standard deviation of the sample. But a question becomes, how close will the sample means be to each other? And how close will the sample means be to the center of the population parameter of mu? That's the big question. We want to know how close x bar is going to be to mu.
The answer to this question lies in the standard error of the mean. So the standard error of mean is a measure of accuracy and precision. Right? Standard error of the mean is a measure of the spread of the sample means from the true mean. Its equation is given by this. It's the population standard deviation divided by the square root of the number of samples that are being used. And that's going to give you the true standard error of the mean. And again, n here is the number sampled, not the number in the population. So what this is giving us is the standard deviation of something called the sampling distribution, which I'll show you an example of on the next slide. A sampling distribution is the distribution of the means of a sample taken from a population. And so the standard error of the mean, you'll generally won't know the true standard error of the mean because you won't know the true standard deviation, right? You don't know the population standard deviation. And so you'll be estimating it. And standard error of the mean can be estimated with sample estimators. So you would have your sample standard deviation, the number in your sample, and you would get that to estimate your standard error of the mean. This is the formula most often used to calculate it. And ultimately, it tells us something a little bit different because it tells us how far the population mean is likely to be from the sample mean, whereas this is telling us how far the sample mean is from the population mean. So they're kind of reverse versions of each other. We'll go into this more in a later module. And so it plays a fundamental role in understanding confidence intervals. So let's talk about a sampling distribution. It's a very important thing to understand. So if we have a population with a mean of 10 and a standard deviation of 5, and we take a bunch of samples, and in each sample we have 5 data points. And for each of those samples, you'll have an x bar, which is a measure of the mean of the sample, and you'll have the standard deviation of the sample s. And so using the population mean and the population standard deviation, we can calculate this standard error of the mean. So let's get a visual representation of what all this means. So if we have a distribution of data here represented by this normal curve, and that distribution of data has a mean of 10 and a standard deviation of 5, right? And we're going to take samples, and you can see 5 dots down here, 5 with an n of 5, right? And that sample has a mean, which is this vertical red line here, right? And so that mean, that sample mean falls close to the population mean, which is 10, but it's not exactly, right? And so each time that we take a sample, we're going to have a mean that is close to the population mean, but not exactly on it, right? And so if we do this over and over again, taking 5 samples and recording the means, and now over here on the right, I'm recording where the means fall and generating a histogram of where those means fell. And you can see they're hovering around 10, but they're not exactly 10, all right? And so our data had a standard deviation of 5, right? But this distribution of sample means has a mean of 10, but it has a standard deviation of our standard error of the mean, right? Its standard deviation is equal to 2.42, and if we did this enough times, it would be equal to 2.23, right? And so that's what the standard error of the mean is describing. It's describing how close these sample means end up being to our true mean. And so an important property of this sampling distribution is that it is making a normal distribution, right? Our data was normal, and now our sampling distribution is normal. This is important because the normal distribution has some useful properties. And that's that because we know its distribution, we know how likely the sample means are to fall close to the population mean, right? And so in this case, it's about 70% of the 70% of the sample means are falling within one standard error of the mean, right? And 95% of the sample means are falling within 2 standard error of the means, and almost all of them would fall within 3 standard error of the mean, right? So that's the properties of the normal distribution, and because the normal distribution is something that we know this about, it makes it very useful. And so if you take larger sample sizes, right? So if in each sample, instead of having 5, we have 50, right? You're going to get a sample mean that is more likely to be very close to your population mean. And so if we play this forward now, right, we're getting this very tight spread of the sample means around the true population mean, right? And it's predicted to have a smaller standard error of the mean, which is a smaller standard deviation of this normal curve, which is still a normal curve, right? But it's a very tight normal curve around 10, right? And its standard error of the mean is 0.71, which means the standard deviation of this normal curve, the standard deviation of this population is 0.71. So this together is really useful. We can use our concept of the standard error of the mean, right, which is showing us the spread of the sampling distribution, combined with the fact that the sampling distribution forms a normal distribution, which we know the properties of, and these properties are here, to give us an idea of a confidence interval. And so if we look at this equation, right, the confidence interval here is going to be the population mean plus or minus z times the population standard deviation divided by the square root of n, right? So what is z? So z is just a proxy for the number of standard deviations from the mean in a normal distribution. So if z equals 1, it's 1 standard deviation above the mean. If z is negative 1, it's 1 standard deviation below the mean. Right? You might recognize some of these frequently used confidence intervals, right? Because of these properties that we know. Now, 95% of the probability distribution for a normal distribution falls within plus or minus 1.96 of the mean, right? 95.5 falls within 2 standard error of the mean, right? So 1.96 is 95%, right? So what this confidence interval is telling us is how close our sample means are going to fall close to the true mean, right? So if you have the true mean and the true standard deviation, the population mean and the population standard deviation, you can now have an idea of where your how likely it is your sample is to be close to these true means and true standard deviations. But you might have noticed that all of this hinges on this assumption of normality, that the sampling distribution will be a normal curve, that the distribution of sample means will form a normal curve, right? And this isn't always going to be the case. So let's talk about when you can assume and when you cannot assume normality of the sampling distribution.
And that's why we need to discuss the central limit theorem. So let me first give you some properties of normal distributions. If your data is normal, distribution of sample means taken from that data will also be normal. And if you add two normal distributions, the result is also a normal distribution. But what if your data isn't normal? When is my sampling distribution normal? It's going to be normal when my data is normal. But even if your data isn't normal, your sample distribution probably is. And the answer here is the central limit theorem. When you have greater than 50 samples, the sampling distribution is probably going to be normal even if the data is not. This is due to the central limit theorem. The central limit theorem says that if you have a population that has a mean and a variance, the sample distribution will trend towards the normal distribution as n goes towards infinity. And that means any distribution. Binomials, exponentials, Weibels, parabolics, anything that you can think of will have a sampling distribution that will trend towards the normal distribution as n goes through infinity. The only requirements here is that it has a finite mean and a finite variance. There are some that do not, but you won't be dealing with any of them in this course, and you'll probably never see one. The further the distribution is from normal, the larger the n needs to be before the central limit theorem is going to fix it. I gave you an n of 50, but that's not hard and fast. 50 is pretty high. You'll see 20 or 30 estimated in a lot of places, but sometimes it'll need to be a little bit higher than that if your data is extremely non-normal. So you might not believe me, but let me show you. So say we have an exponential distribution that has a mean of 10 and a standard deviation of 9.8. We're going to take samples of 50, take those means, and build a sample distribution from those. All right, so let's play this forward. You can see that this is an exponential distribution, but each time we average 50 of these exponentially distributed points together, and then we record where those means fall. And as you can see, they start to form something that approximates a normal distribution. And it has the standard deviation that we would expect predicted from the standard error of the mean. So this is about as not normal as you can get. I mean, this is totally skewed all the way to the left, cuts off abruptly at 0, and still, when we take a sampling distribution and we look at how those means are distributed, it's forming a normal distribution. And that's for an n of 50. But let's say we decrease that down to an n of 5. This is below where the central limit theorem should be doing enough to make the sampling distribution normal. But again, when we play things forward, there's a wider standard deviation, and it's forming something that is normal-ish, but it's not really. It's skewed to the left. So it tries to become a normal distribution, but it's not quite enough samples to have the central limit theorem take over and move it towards a normal distribution. Okay, so this is really powerful. The central limit theorem is essentially saying, as long as your n is high, your data is going to end up being normal. So even if you don't have normal data to begin with, you can use any statistical analysis that involves comparing means. That involves t-tests, confidence intervals, ANOVAs, general linear models. Pretty much everything we see in this course, if your n is above 50, you're going to be okay using it. So when does the central limit theorem fail? I told you it fails with low n's. I've told you it may fail for medium n's with highly skewed data. And it will definitely fail if the data has an infinite mean or variance, such as the Pareto distribution. But then you have to ask your question, all right, so what if I have an n of 20? How far is my data from normal? There's a lot of tests for normality, and we'll focus on two for this course. Quantile plots and the Shapiro-Wilks test. We're going to cover the Shapiro-Wilks test a bit later after we know what hypothesis testing is, which will be introduced in some of the coming lectures. For now, let's focus on these QQ plots. So what are quantile plots? Well, quantiles, you might recall from our last exercise, and you'll especially recall from when you learned the median. The median is a quantile. It's the 50% or 0.5 quantile to be exact. Quantiles basically say X% of the data is going to fall below here. So the median said half the data is above, half the data is below. But the 75% quantile says 75% of the data is below this, the 25 says 25% of the data is below this, etc. And in R, it's pretty easy to calculate quantiles. You just use the quantile function, you put your data in here, you type in 0.5 in the second column, or 0.7, or whatever quantile you want to generate. Calculating quantiles is a bit more complicated, and you don't have to worry about how to do it. The median is halfway. The others, you can, if you ever need to do it by hand, you can look it up. So what about a QQ plot? So the steps here are you generate quantiles from your data. You can do it using R. You can make as many quantiles as you want. If you want 100, you can do 100 percentiles, or 4 quantiles, or 10 quantiles, whatever it is you want to break your data into. Then you find a normal curve, and you break that into the same number of quantiles that you broke your data into. And then you plot them. In R, you can use ggqqplot. It's from the ggpub-r package, which you can install. It's a bit better than the QQ-plot that's built into R itself. And it'll generate something that looks like this. So here's the normal data that the normal curve data that I was showing you guys earlier. You can see that there is the data plotted on the y-axis, and our normal curve has been plotted on the x-axis. Each one of these points is a quantile. And so you're seeing the 50th percentile from the normal curve plotted against the 50th percentile of the data. If the data is matching a normal curve, it will line up on a 1-to-1 line with the normal curve. If it's deviating, then it'll end up being above or below. And you can see these gray error bars here. If many of the points are outside of the gray, that means that it's most likely not normal. If everything falls on the 1-to-1 line like this does, then it's a good fitting normal distribution. So let's go back to some of those non-normal distributions we were looking at before. Specifically, this one where we have an exponential distribution here, and we were taking samples of 50 and generating a sample distribution over here. So if we do the quantile plot for the data on the left, it ends up looking like this. So now you can see this QQ plot deviates extremely heavily from the 1-to-1 line that would indicate that it was normal. This is a very non-normal set of data. But if we make the same quantile plot for the sampling distribution, you can see it does a pretty good job at hugging the 1-to-1 line. It is in fact a normal distribution. But what about for this other one, where we were only taking samples of 5 from our exponential distribution? Here, the plot didn't look quite so normal. So if we do a QQ plot for the data, again, it's extremely not normal. But if we do a QQ plot for this slightly skewed distribution, you can see that the data has a bend that curves away from this 1-to-1 line, indicating that it is deviating from a normal distribution. It's not as far away as this data, but it's definitely far enough away that it's not a normal distribution. So, I mean, that's QQ plots. That's how you test for normality, and that's the central limit theorem. You're going to see a lot of normal data in biology. There'll definitely be times where you see non-normal data, but the normal distribution tends to show up. And that's because the central limit theorem extends even beyond just sampling from a single population. Biological data often ends up being normal. Things like height, or height is the one I can think of. Weight, the number of RNAs in a cell. Lots of things in biology end up being normal. And that's because in biology, there's a lot of averaging across time and number. The number of RNAs that are being generated are being averaged over time. The number of proteins that are being generated from those RNAs are being averaged over time. The number of cells that are signaling to other cells are averaging the proteins that they're releasing, and the organisms, the cells are all averaging into organisms. So there's tons of steps where you're taking lots of little discrete cells and averaging them together, lots of different inputs to generate larger distributions. And just like sampling from one distribution many times can generate a normal distribution, sampling and averaging together from many different non-normal non-normal distributions can also generate a normal sampling distribution. So to illustrate this, say we have 3 cells, and these 3 cells are producing they have non-normal production rates of RNA. Sometimes they're producing a lot, sometimes they're producing a little. It's bimodal, it's off and on, and so some of them will have a lot of RNA and some of them will have less. Well, those cells will go on to produce different amounts of protein, but if they were all signaling to the same cell, this cell would essentially see an average of all of the different cells' proteins that they were producing. And so in this way, you would be taking multiple samples and then creating an artificial sampling distribution that another cell is looking at. And in that way, you could take non-normal production rates of RNA and turn it into normal distributions of signaling molecules. So that's the central limit theorem in practice in biology. All right, so I think we're going to stop it here. I'm only doing one lecture this week because this one had a lot packed into it, but I think all of the concepts needed to be presented together so that they could all stick. Yeah, I hope it was very clear.